After series and parallel systems, let's look at the general case of k out of n active system, but we are not talking about load sharing yet. So all the elements of the system are mutually independent. So recall that we discussed at the beginning of this lecture that the system reliability is equivalently stated as the probability that at least k systems are up, k units are up of the system at time t, or t sub parenthesis k, so the kth order statistics is at least t or higher. So now if the elements are IID, which is what we assume for this part, we have a simple binomial representation of the system reliability, and you can clearly identify the binomial sum, the sum of the binomial PMFs, I going from k to n. At least k elements must work. So now if in addition, if all the TTFs are exponential and independent and IID, so they have the same lambda, so under that simplifying assumption, we can find the system reliability and the system MTTF, the mean time to failure. So the mean time to failure, as always, is the area under the reliability curve, and we can go through the steps, and we write out the exponential PDF out, the exponential form of the reliability for each element. So that comes to, by substituting nu for exponential minus lambda t, when lambda is the individual parameter of the TTF, it turns out that we come to a form which is the beta function, and the beta function is the ratio of involving three gamma functions. So we have gamma I, gamma n plus 1 minus I, and gamma n plus 1 in the denominator, and gamma function for integer values is nothing but the factorial. So gamma n is n minus 1 factorial. With that definition, we can come with the final solution, which is the mean time to failure for the system is the mean time to failure of the element times an amplification factor, which is sum of 1 over I going from k to n. So for such k out of n active systems with independent components, let's solve a couple of examples. The first one, let's take a minute to read the problem. So it's a 2 out of 3 system, and each time to failure is exponential in nature. So the probability that any one of the elements is working at time t is exponential minus lambda t, which we call p sub t. So that is the success probability for each element. Now let's define x of x subscript t as the number of roots that are okay at time t. So xt is binomial, as we saw in the previous slide, with parameters pt and n, and the system is okay at time t is the probability that xt is at least 2. So with 3 elements, this is xt equals 2 or xt equals 3, so we can add the two probabilities, and if we do the algebra, it just comes to thrice p square q plus p cubed, where q is 1 minus p, and the final solution is given as a difference of two exponentials. The next problem is not an exponential distributed element time to failure. It now has Weibull distributed time to failure. So let's take a minute again to read the problem, and then we will solve it step by step. If you would like to solve it yourself, please pause the video. So what we have is a 3 out of 5 system. Each TTF, as I said, is Weibull distributed. So let's write that out. So TI is Weibull with a mean of 2 years and a COV of 30%. So we need to find the two parameters, Weibull parameters. So we need U and K. We have looked at this graph before. So this is a convenient way of finding K from the COV for a two parameter Weibull. And for this set, we find that K is 3.72 and U is 2.216. So the Weibull complementary CDF, the Weibull reliability function, is exponential minus of T by U to the power of K. So plugging in the values of T and U and K, we just found out at 1 year, this P of T, which we are calling P1, is 0.9495. We'll also need its complement Q. So let's define Q1 as 1 minus P1. So with all this information, we are now ready to find the system reliability. So as we did in the previous example, XT is the number of pumps that are okay at time t. So what we know now is that XT is binomial with two parameters, PT and N. For this example, N is 5, and we just found out PT, which is 94.95%. So the system is okay at time t. It's a 3 out of 5 system, so XT is at least 3. So we need to sum the three probabilities. XT equals 3, then XT equals 4, and XT equals 5. So that would be the sum of the three binomial PMFs. And if I have done the algebra correctly, we should get an answer of 0.999. So which is a very highly reliable system, provided obviously the pumps actually operate and fail independently. This, if you compare with if all 5 pumps had to work, then we would have a much lower reliability, because we would only have P to the power 5, which is about 77%. So this is the benefit of adding redundant elements. And as I said, if the elements indeed operate independently, there is no common cause failure, there is no overloading if successive pumps fail, then we can expect an increase of reliability from 0.77 to about 0.999.